This is the atmospheric dispersion spreadsheet, and I just want to quickly go through to show you how to complete it. This version is mostly complete. Your version won't have any numbers in these tables, but you'll be able to fill those in yourself. I just show you how to start off doing it. The way the spreadsheet works is that over on the left hand side there's calculations to work out the standard deviation of concentration within the plume, both within the y-axis, so across the plume, and also vertically through the plume. So you can imagine a normal distribution or a bell curve that runs through the plume vertically, and we need to know what the standard deviation is of the normal distribution in order to be able to plot it and then work out what the concentrations are at those points within the plume. And similarly across the plume as well, we need to know what the standard deviation is of the concentration distribution across the plume. If we know the standard deviation, then we can plug that into the formula for a normal distribution and work out the concentration at any point along that curve. So the first part is to work out the standard deviations, which is done down here in this part of the table. So standard deviations are worked out here, and then the equation for the normal distribution, or a version of it, is then written into these tables, and these refer to these standard deviations. Okay. The other parameters that they need to refer to are written in here in the input data. So there's input data here and standard deviations here that will be referred to by the Gaussian formula that goes in here. And because we've recognized that different stability conditions can exist in the atmosphere, this is vertical mixing stability, we've got three different stability classes of stable, neutral and unstable. So we've got three tables. These tables you should recognize as being maps. This is distance downwind, this is distance crosswind, and then the concentrations get filled in here. Well, the dispersion is going to increase with time, and effectively that means it's going to increase downwind, and the age of the parcel of air as you move down is going to increase as you move downwind. Dispersion is also going to be influenced by the stability, and we've got three stability classes. So we're going to have to work out standard deviations at different distances downwind and also under different stability conditions. And that's why we've got this table here, because there are three stability conditions and then there's a standard deviation for each distance as we move downwind. These equations have been worked out for us and we just need to copy them in. So this column is stable. We've got the dispersion, there's a standard deviation in the y direction, so that's the across the, so here we go, we just need to copy it, stable, copy that, copy it in here, okay, check that it's referring to the right places, so it needs to refer to the distance, which it does. There's a $sign in front there because all of these cells, if we copy them across, all of these cells will refer to the same column for the distance, column A. Okay, well that's correct. Now we need to get the standard deviation in the Z, so standard deviation for the distribution in the Z direction. We have the formula for that under stable conditions. Copy that in. And then we can copy both of those down, either just drag that or double click it to copy it down. This formula gives us the concentration within the plume. So if we know the standard deviations for any one of these normal curves, whether it's in the crosswind direction or in the vertical direction, if we know the standard deviations, then we can plug them into a normal distribution and work out the concentration at any particular point. So again, we've been given the equation to copy in, and we should copy it in where it says stable conditions at minus 50 meters crosswind and 0.1 meters downwind, which is this corner. not minus 50, it's minus 500, but we should be copying it in here. Just check that it's referring to the correct dispersion coefficients, the correct standard deviations, which it is, stable, so it's referring to the right ones. It's referring to the wind speed that we get under stable conditions, which is here, and this is the stack height and the measurement height. Okay, so it's all correct. Okay, and then again you can copy that down and copy it across. These tables should all be formatted to just have 2 decimal places, so let's redo that. 2 decimal places, okay, and then we can put the grid lines back in as well. Okay, so we've copied those in, and these graphs have been drawn, and they've automatically drawn the graphs in. Now you can draw the graphs yourself. The other video shows you how to draw those. Let's see what we've got. There's a graph here which is plotting the centerline concentrations under the 3 different stability conditions. So that's these 3 tables here: the stable, the neutral and the unstable, and the center line is 0, so it's just reproducing that data. So you can see that's what's going on. Click on that, this line. So that's all this graph's doing, it's just letting you see this is the centerline concentrations, and we can see that under these conditions the ground level concentration is 0 when you're very close to the chimney under the stable conditions, and then it starts to go up very high and then starts to come back down once you've gone just about 8 or 9 kilometers away. It starts to decrease, but between 2 kilometers and 9 kilometers it rises very steeply. That's on the center line. Okay, and you can see that shown in these graphs as well. This is the stable, neutral and unstable. When you draw yours you need to make sure they're labelled, but under stable conditions you can see this is 0, so this is where the chimney is. Concentration is very low because under the stable conditions the plume isn't touching the ground. There's no mixing under the stable conditions, and it's only when you get further away that actually it starts to hit the ground. And you see, we looked at that from the line graph. From 2 kilometers it starts to increase. Under neutral conditions there is some gas concentration near the plume, because under the neutral conditions there's a certain amount of mixing, and similarly under the unstable conditions the plume is getting to the ground, but then as you get further away, because the mixing's gone on, the plume might be getting to the ground, but it's so dilute by the time it gets to the ground that it's showing up as very low concentrations. So you've got this balance of being close to the chimney, and if you're close enough to the chimney the plume doesn't get down to you, but unless there's very, very intense mixing, and if there's intense mixing then it gets diluted very quickly as well. So you can see what's going on there. Now the parameters that you can change in here are the stack height, and you've been asked to investigate what happens when you have a 20 meter or a 60 meter stack height. We're interested because we've got these two towns, Filth and Rich Town, and we've got, this is the output. So these cells are extracted from these tables because you know the position of Filth and the position of Rich Town. They are marked on here. 200 meters crosswind and 3 kilometers downwind is Filth. I can mark them on again here actually. 200 meters, 0 crosswind and 6 kilometers downwind is Rich Town. So you can see them marked on there, and if you click on here, these cells just refer to these, so it collects the data together in a little table, so you can get the concentrations under the different conditions in the two towns. The other one that's on here is the average, we should just talk about. The average is calculated in this table, and you can see how it's done if you just click on one of the cells. The average is taking the concentrations from each of the 3 tables, so from here and here and here, but they need to be multiplied by the amount of time each of those conditions occurs. So unstable, neutral and stable, and that's what this formula is. So you can see you've got the concentration multiplied by the amount of time that it occurs, the proportion of time each of these occur, and that's what's put in for the average. Okay, and those numbers are then extracted into this table. So what you can do is play around with the stack height. You've been asked to investigate what happens with a 20 metre and a 60 metre stack height. The other box here that you can change is the height at which the measurement takes place. Now you're not asked to do this, but it's something that you might, an understanding of what's going on. It's set at 0 because we're interested in the concentration at a ground level. That's 0 metres above the ground, but you could find out the concentration at different heights above the ground as well. So let's change the stack height from 20 metres to 60 metres and see. You need to remember that these graphs are auto-scaling, so they don't necessarily have the same scale when you come to look at them. The same colour doesn't necessarily mean the same concentration. You can change that, and that's discussed in the other video about making them fixed, fixing the ranges of the concentrations, but these are auto-scaling. So under stable conditions, again, there's no concentration near to the chimney because the chimney is even higher, so the plume doesn't actually reach the ground until it's much further away. And then when it does reach the ground, though it's further away, because it is further away, there's much more dilution that's gone on. So you can look at this centerline concentration and you see the concentration is very low. Under neutral conditions, again, these concentrations are all much lower than previously. In the unstable conditions, there's enough mixing to get some gas close to the ground near the chimney before it's been diluted. So your undiluted gas is reaching the ground. So you've got the highest concentrations under the unstable conditions. So it's bad to live near the chimney on that occasion. But you can just flip from one to the other, from the 20 metre to the 60 metre. And see where it's best to live, and the question that you're asked really is to decide whether or not it's worthwhile building a 60 metre rather than a 20 metre stack. To give some context for this, you've been given the regulations that are in place in Filshire, which are actually similar to regulations that are used in real parts of the world, such as in America. The average annual exposure limit is 0.1 milligrams per metre cubed, but there are also limits for shorter periods as well. Over a 24-hour period, there shouldn't be an exceedance of 0.4 milligrams per metre cubed, and over a 3-hour period, it shouldn't be more than 1.5 milligrams per metre cubed. So you can set these readings that you've got into some context. You can also change the stack height to something other than 20 and 60. If you try 5 metre stack height, it should be much cheaper to build, and see what happens then. You see the concentrations go up massively. They're as high as 100, 150. In our towns, again, they've increased massively. They're not as high as 150 because the towns aren't located in the worst places, but they're still much, much higher. So you can play around with that. Go back to 20. In your discussion, and therefore this will control the results that you should actually present as well, you should be trying to show your client what the impact of a 60 metre or a 20 metre stack height will be on the two towns, Filth and Richtown. So that's what you need to pull out from the spreadsheet. And then you also need to really talk about further work, and you can do that by considering the measurements, well, the predictions that you're making for Filth and Richtown for different stack heights, but also comparing those to the regulations and having some understanding of the way the regulations work, in as much as that the annual average concentration isn't the only guiding factor in this. Sulfur dioxide exerts its effects particularly on acute cases, so people don't die of sulfur dioxide annual average concentration. Typically they die of more acute concentrations, so the higher concentrations. And what we have again is an issue of resolution. Now you could have just presented, or you could just present the average annual concentration and make a decision on the basis of the average annual concentration. That would be simple. However, some understanding of sulfur dioxide and its impacts would suggest that that isn't the appropriate thing to do, and really you need to try and have some understanding of when you might have acute events. The reality is you have some indication that that might happen, because you aren't just looking at the average annual, you have split it down. In the same way as in the previous exercise, you looked at spring and neap tides, you looked at different conditions. Here you've looked at different stability conditions. So you've increased your resolution in terms of splitting the year into 3 stability conditions, and you get different results under those conditions. And that's what you should be looking for. Do you get different results under those conditions? Under those conditions, and under the separate conditions, do we get exceedances of the regulations? Or even if the numbers are different, it indicates that the resolution that you're actually working at probably isn't high enough. Really, if you're looking for times when you're going to have much, much higher concentrations, you're going to need to separate your stability classes into higher resolution than just like these 3 broad groupings of stability. And really you need further investigations of the meteorology in the area, and particularly conditions where you might get extreme concentrations, and you should think about when that might happen. You've got an idea about it from your general knowledge of meteorology, and using this model as well gives you some further backup for that sort of thing. When would you get highest concentrations? The two processes that you need to think about are, one, the plume getting to the ground, but also the process of dilution as time goes on. So if the plume can stay up for longer, then it can get diluted more. Okay, and what are the controls on that? What might be the worst possible case? You can't know what that is from the investigation you've done so far, but you should be making some suggestions as to further work in order to identify what the worst cases might be.